Hello everyone. So in this recording, I'm going to talk about random variables, which is the topic in chapter 2, right? So what is random variables? Earlier, we talked about outcomes. And for example, if I toss a coin, the outcomes can be head or tail. If there's a game of football or soccer, the outcome of the game is either one team wins or the other or a tie, right? Um, in these simple examples, we can represent or we can find the probability by using the principles, the basic principles, and or the intersections and the union, and we can also implement or apply some of the principles as well that or basics that we talked about, which is if two events are disjoint, right, we can add them without considering the intersection between them. If they are two independent, then we can calculate the intersection by multiplying the events or the probabilities, I mean. So for a quick reminder, if P union A or union yeah uh, B union A or A union B, we can use or find the probability by calculating the probability of A plus probability of B minus the intersection between them, which represent AND, right? If they are disjoint, we can simply ignore this because it's 0 and it's simply BA plus BB. For intersections, if they are independent, A and B, we can multiply their probabilities. So we saw some of these basics, right? So keep these in mind. If I want to find the probability of three heads in a coin toss, so I toss the coin once, I toss the coin twice, three times, and I want to find the probability of heads coming three times in a row. In that case, I will say, well, the probability of head first and then head second and then head third. So that will be head and head and head. Right? Each one of these, because they are independent, right? So every coin toss is independent of the other. So it doesn't matter how many tosses you have. Every toss, the coin does not remember what the result was time. So it's always 50-50. So that means that the outcome will be or the result of the probability is P head multiplied by P head multiplied by P head, or if I do that numerically, will be half multiplied by half multiplied by half, 3/8, right? Okay, so if I continue the experiment, what if I want to find the probability of one head in three head toss, a three coin toss? So at some point, I may find that it's easier just to calculate or to represent the number of heads in a three coin toss as a variable that has a value from 0 to 3. So it's three coin toss. So I can see no heads, I can see one head, or I can see two or three. So rather than doing this, I'll say, well, how about I'll represent the number of heads as x here, and the x take value of 3. This means that this is equivalent to head and head and head. How about x equal 2? So this means that I can have the head first, and then head second, and then tail. Is that it? No, there is also other possibility. The other possibility will be, so that's, or I have head and tail and head, or tail first, then head, then head. So I did all of this, so I end up like, let's simplify it, right? First, these will be, all of these are disjoint and mutually exclusive, so we don't have intersections between them, right? So we could simply say the result will be head, head, tail plus probability of head, tail, head plus probability of tail, head, head. Remember, if they're not disjoint, we have to subtract the intersections between them, right? So and it gets the formula gets a little bit longer. All right, and for each one of these, as we did before, this is the probability of head multiplied by probability of head multiplied by the probability of tail, and we'll finish. We end up with half, since all the heads and tails have the same probability. We end up with 3/8, right? And as you can go back and see from the notes, well, look how much we actually simplified, but we can calculate all of this using the basic principles that we learned. But we can just simply say the probability of x equals 0 is 1/8, x equal 1, where x is the number of heads, is 3/8, and we'll continue like this. This is what now we learned two things. First is the random variable is, we can use it to represent, if we have, before we have a sample space, and each sample space had a probability, right? So the sample space omega is the set of all the outcomes, and each outcome has a probability, right? We have all of these events when they get complicated. So we have tail and tail and tail, head, tail, tail. So rather than representing them with a really large set with a lot of descriptions, we can represent them with a random variable where x here represents the number of heads, right? We can also say x represents the number of tails, right? X, it's a random variable. We can assign it to anything. Okay. So in many situations that we will deal with, the random variable has, when we find out all the probabilities for all possible values of the random variable, we get the mass function, right? So here, in this example, all possible values of x are 0, 1, 2, 3. These are all the possible values. All of these, the the probability is 1/8, 3/8, 3/8, and 1/8. So that's we can call that as the mass function, and we represent it by the p of x here. And notice that we are using the square bracket, what they call them, round brackets, instead of the square brackets or the squiggly brackets. So we are using different notation here. All right, so And we know from the basic principles as well that um, for the sample space, if we um, add up all the probabilities for a sample space, all the outcomes, we end up with one, right? So a game, what is the probability that the outcome will be red wins or blue wins or a tie? So that's a one, right? Because there's no other possibility. What is the probability that there's no outcome? Will be zero, because every game has an outcome, right? So every the sample space has a phi has a null probability, which is always zero, and the probability of all outcomes combined is one. For a mass function, if I add all the results, I'll end up with 1. So 1 8 plus 3 is 4 8 plus 3 is 7 plus 1 is 8 over 8 is 1. Right? If I add all possible numbers up to a certain number, so if I say the probability of x equal or less than 0, that's 1 8. If I say what is the probability that x less than or equal 1, right? So it can be x can be 0 or x can be 1. So that's the probability of x equals 0 plus the probability of x equal 1. Since these are mutual exclusive uh, events, I can add them up without thinking about subtracting, right? Subtracting the intersection. So they are mutually exclusive. So it can be either 1 or 0. It cannot be um, 2 at the same time, right? So this is 1 over 8 plus 3 over 8. We get into 4 over 8. Probability of x less than 2, this will be and now I can use the simplified version of it, so I can say p of 0, p of 1, p of 2. So that's, by the way, that this term is equivalent to this term, right? So these two are equivalent, just the notation now we're using simpler, right? Because it's gonna get really tedious if we're gonna do x equal every time. So that's 1 over 8 plus 3 over 8 plus 3 over 8. That will be 7 over 8. And finally, x equal less than or equal 3 will be 1, right? All right. So this, we'll call it the cumulative distribution function. And we could represent it by x equal or less than small x, or I can represent it simply by the capital F here. Okay. So this will be F0 or F1 or F2 or F3. In many cases, the calculation of the cumulative distribution function is a lot easier than calculating the mass function, right? So, and we will see later when we talk about tables, probability tables, we will look for most of these tables are they give us the cumulative distributions function, or CDF for short, rather than the mass function. Right? And all the numbers will add up, so the maximum will be 1, right? So when we add up all of the probabilities, we'll get 1. So here is the official definition of the CDF. Is f of x is the sum of all probabilities up to and including x. Okay, if I am given these functions, if I'm given x and let's say a table, sorry, so the table just give me x and f small x here. Right, so for 0, this is 1/8. For 1, this is 4/8. For 2, this is 7/8. And for 3, this is 8/8 or 1. Right? And somebody asked me, what is the probability of x equal? So I can represent it either by saying, what's the probability of 0, which is similar to x equals 0. So that's simply 1/8. But what is the probability of 2 here? So in this table, there is no, I need to find the probability of 2 by using the CDF. F of x here represent the probability of x less than or equal certain value, right? Try to differentiate between the small x and capital X. So to find or to isolate the probability of 2 only, so I have to do f2 minus f1. Why? All right. This is actually the probability of something, all the, let's say all of these green probabilities, right? And I want to find only the probability of 2, so I have to subtract these probabilities. So that's why I need to do f of 2 minus f of 1, so that will be 7/8 minus 4/8, and end up with 3/8, which is what we know is the actually the probability of 2 heads, right? So that's one of the things that you need to do very often, is to find the probability of x equal something by using the CDF. The CDF defines x is less than or equal something, right? So that's, I don't know if you get this idea quickly, but the probability of, let's say if I want to do it in a general form, the probability of p or p of x is f of x minus f x minus 1, right? So probability of 2 is f2 minus f1. Probability of 3, by the same idea, is f3 minus f2. And from the table, we can say that f3 is 8/8 minus f2 is 7/8. So this means that it's 1/8, right? if I'm trying to do the opposite, so f2, this means that it is the sum of all values, all the probabilities up to 2, right? So this means that it's the probability of 0 plus probability of 1 plus probability of 2. Right. So let's move on to something different then. All the, or maybe something also we need to talk about is the range. So we calculated x as one value. What if I want a range? So in this case, we're going to talk about what is the probability that x is between 3 and 1. So in a coin toss, it's like saying anything but all tails, right? So we could say, well, this is exactly like f of 3 minus f of 1. So in this case, well, we have to be careful here. This is actually, it has to be something between 3, something between greater than 1 and less or equal 3. So that's the formula. If I want to do the probability as I did before, probability of 1 like this, the way I do it is, you know, just in case I get confused, I draw it. So these are the values 3, 2, 1, 0, or you can do it the opposite way. Let's do it the opposite way here. So 0, 1, 2, 3, and I need everything including 1 and 3. So I need the probabilities of these values. So I could say here that I am excluding only 0. So it's f of 3 minus f of 0, and the result will be 8 over 8 minus 1 over 8. That's 7 over 8. How about this one? This one actually, it says, if I going back to my drawing, I will say this includes 3, right? And anything greater than 1. So everything from something greater than 1 up to 3. So this includes these values only. And that's why if I take f of 3 and subtract f of 1, which gives me this part here, so I get 8 over 8 minus 1 here from the table, just to remember, 4 over 8. So I get 4 over 8. Okay. So this, you're just putting all the values and trying to understand the, or be careful about the greater than or equal and less than or equal or less than. So be careful about these things. Okay, so all the variables that I used are discrete, right? Discrete doesn't mean integer, but it means that I don't have a definition of anything in between. So it's either 1 head or 2 heads or 3 heads or 0 heads, but there is no such thing as 1.5, no such thing as 1.57. So it's either 0, 1, 2, or 3. Right? So a lot of random variables are discrete. Uh, Again, discrete doesn't have to be integer, so it could be, let's say I am talking about time and I am calculating time based on minutes. So the probability of having an event that happens in the first minute or second minute or third minute. So all of these are integer values. Nothing is defined for 1 minute and a half. Right? Sometimes the random variables are continuous, right? So continuous means, let's say wait, let's say a time, if I want to calculate the time accurately, not just as minutes. Um, so time usually it can be 1.67 seconds or so. I could calculate time as a continuous random variable where time can be anything, right? Um, So you see here a lot of time, voltage, temperature, all of these are values that can be continuous. And the continuous can be converted into discrete. Let's say I am calculating temperature. A temperature as a physical phenomena can be anything, right? But if my thermometer shows only um, temperatures in discrete numbers, it will show me temperature as 19, 20, 21. It doesn't show anything in between. So that's the difference between discrete and continuous. So sometimes we need to deal with random variables that are discrete. Sometimes we need to deal with them as continuous. And in the remaining of this chapter, at the end of the chapter, or the second half of this chapter, we'll be talking about uh, distributions like this that are discrete. And the next chapter will talk about continuous distributions. Right. So if I talk about, we talked so far about random variables that are independent or outcomes that are independent. And some of them will depend on each other as well, like the example of flights being delayed or being arriving in time or departing in time, right? So we have this issue of dependence or independence. Um, when we talk about distributions, we get to discuss the idea of what is the distribution of two random variables happening at the same time, right? If you are looking for or measuring or talking about performance of computers have the CPU, have RAM, have a hard drive, right? Um, and if I look at a computer at any specific time and I could represent the CPU speed as a random variable. I could also represent the size of the RAM as a random variable, right? And I could represent them as two variables and with joint random distribution, with joint distribution. So for example, say what is the probability of the CPU speed or the CPU load is 0.7 and the RAM is free RAM is 1.2 gigabits. So in that case, I will consider instead of the one random variable, I will consider random or a random vector. So the vector here in this example is just two variables, but the vector in general can be multiple variables. For this course, we'll deal with just two, right? So two random variables, each one of them can be dependent or independent of each other. You could say that the CPU, every time the CPU load is high, this means that probably we're using more memory. But the CPU could also be high because it's crunching a lot of numbers. The memory is not much, is not being used much, but it's just crunching a lot of numbers, right? So these two variables can be dependent or can be independent. So that has nothing to do with the joint distributions. Joint distribution just means that we are talking about distributions of two or more random variables at the same time, right? Okay, so to represent two or distribution or probability of two random variables, we represent them by something like px comma y, which is equivalent to px capital or capital Y equal x and y. So in this case, let's say x is the CPU and the y is the RAM. So I could say the probability of 0.7 and 1 meg is 0.2 and 0.6. So this being the CPU load, this being the free memory, and these are the two probabilities. Right? Okay. So some of what we talked about earlier applies. So the total of all the probabilities of the joint this or the pair or the vector, random vector, all add up to 1. Right? And let's say I'm representing these two random variables, x and y, as a table with x being the rows and y being the columns, and I'm giving each one of them certain values. They don't have to be the same range, by the way. As we saw earlier here, the CPU load can be any number from 0 to 1. That's the load, right? Or 0 and 100% if you want to think this way. The memory can be 0 to 5 gig. So the range or the value that x takes can be different for x and y. So let's say x ranges from 1, 2, 3, 4, and y is 0, 1, and 2, right? So in this case, I can have the probabilities of x equal 1 and y equal 0, and I put it here. And same thing for x equal 2 and y equal 0, and put it here, and so on, right? And I can fill this table with all my probabilities. Okay, so if I take a look at this, and if I sum all the values in this row, what I will end up with x sum of, the y doesn't change, right? But now I'm calculating the px and 0, or p1 and 0, py, p2 and 0, and so on, right? So I'll end up with the probability. This is actually the probability of y equal 0. So that's the sum, and this will be the probability of 0. This is not joined anymore, right? So this is just the probability of different values of y. And if I do the same thing vertically, I'll end up with the probabilities of x equal 1, probability of x equal 2, probability of x equal 3, and 4. right? So now I separated the two values, and you can see here the P and the subscript is capital X. So Px alone will be the sum of all the joint probabilities here with a fixed y, and so as the other side. Right. All right, so the next topic will be the independence of the random variables. As I said before, they could be dependent or independent. So how can I test? So to test independence between random variables, uh, it's the same as with the with other examples that we saw earlier. So the p, x, and y can be independent if px, or if the px and y equal px multiplied by py, right? Um, but that must happen in all values of x and y. What I mean by that is, if we look at this example, right, so to verify that x and y are independent variables, then it's not enough that I test only two values, let's say 0 and for x is 1, for y is 2. That's not enough to say, okay, is it p1 multiplied by t2 p2 equal to this value, which will be here, right? If I multiply this one with this one and find them equal, is that enough to verify or to prove that x and y are independent? No, it's not. I have to test all these variables, right? So, but to prove dependence, I have to find only one value that in which these two are not equal. So if I find px comma y equal or does not equal px and py, if I find just one case where these two are not equal, I prove dependence. So it's easier to prove dependence than to prove independence. Independence requires that I test all values, but to prove dependence, I have to find only one case, right? So let's take this example. A program consists of two modules. The number of errors x in the first module and the number of errors y in the second module have a joint distribution, right? And it was given to us by these formulas. Find the marginal distribution. The marginal distribution is px alone or py alone, right? 2, the probability of no errors in the first module, and 3, the distribution of the total number of errors in the program, also if errors in two modules occur independently. So I want to test the independence. Okay, so I will do the same thing as my example here. I will take each one of these values and arrange them in a table. Okay, so let's do this. Put this aside. Or actually just switch to the table here, and we may go back and forth between the two tables, just so that notice that for x the values are arranged in rows and we have only 0 and 1, right? So we have two values, 0 and 1. That's for x. For y, we have 0, 1, 2, 3. Okay, and if you go read P00 and P01 and P10 are 0.2. 0.2, 0.2, and 0.2. P1, P11, P12, and P13 are all 0.1. Okay, and P02 and P03 are 0.05. P01 is supposed to be, I probably made a mistake in the calculations here. P02 and P0, yeah, okay, so this is 0.05. I didn't make any mistake. Okay, good. Right. So, speaking of mistakes, okay, how do I verify that what I did was correct? Aside from, going back and forth to see what the problem is. I can check very easily by looking at the principle that the total number has to add up to 1. Alright, so 0.2 and 0.2 is 0.4, and these two are 0.1, so the total here is 0.5. And if I add up all of these, this will be another 0.5. Column-wise, 0.4, 0.3, 0.15, 0.15. All right, if I add all of these, I should end up with 0.1. Sorry, I should up with obviously 1, not 0.1. And if I add all the columns here, I will end up with 1 as well. So that's 0.4 and 0.3 is 0.7 plus 0.3 between these two, so that's 1. All right, so that's the table. What is the marginal distribution? So here we're adding all the pxy values and fixing the y, fixing the x, going row-wise, adding all the columns. So what we will get is the py. So as with the matrix here, so if I am adding all the columns and fixing the x here, so x is 0 for all of them, right? So I'll end up with px of x. And here so this is the margin distribution. Sorry about the delay, the deletes here. So the px of x distribution is this column, and the py is this row. So we fixed x, and we added all the values of y. So we ended up with x equal whatever we x the fixed is. So we fixed with 0, so we end up with x equals 0. And when we fix x as 1 and sum all the y values, we end up with x equal the probability of x equal 1. Same thing when we do it column by column. We fix y and we add all the values. So y for y equals 0, we add up p0, 0 and p0, 1. We end up with probability of y equals 0 here, and so on, right? So we get the marginal distribution, and that's the first requirement. Second requirement, we want the probability of no errors in the first module, right? So remember, x and y represent the errors for the software errors or the bugs in the first module of the software module, and the second. So they want us to know or to find the probability of no errors in the first module. So this is simply the probability of x equals 0, no errors. So where is it? Well, here it is. It's 0.5. We just found it. We couldn't have found it without finding the marginal distribution first, by the way, right? The distribution of the total number of errors in the diagram. So here, actually, it gets a little bit more involved. So I have x and I have y, and each one of them represent an error in one module. What is the total? So the total, we need to come up with a new variable called z, and this variable represents both x and y. So let's take a look. So assume that z is the variable that represents x and y. And we need to find, before we find the probability, or they ask us for the probability mass function, and I think the probability, or they ask for the probability distribution. All right, so which is the mass function, right? So we need to find p z0 and p z1 and so on. So we know that x goes from 0 to 1, y goes from 0 to 1, 2, 3. So the maximum number of errors in the first module is 1. The maximum number of errors in the second module is 3. So z goes from 0 to 4, right? So this will be 1 and this will be 3. That's so before. So z can be from 0 to 0 to 1 and 4. Okay, so that's our set of values that x can take. So what is the probability of z equals 0? Well, that's the probability of x equals 0 plus the probability of y equals 0. And in this case, it is actually, I probably shouldn't have done it this way. I should have done it as you can see here. Right. So let's go back a little bit and correct this mistake. So that happens. Let me put it back in the basic terms first. Let's have the z equals 0 if x equals 0 and y equals 0. And that's exactly the probability of 0, 0. It's the joint probability, right? And that's from the table is 0.2. So I can use the same idea here. When is the probability of z equal 1? Or what is the probability of z equal 1? So that happens if x equals 0 and y equal 1. It can also happen if x equal 1 and y equals 0. So it's either this or this. These are mutually exclusive, these two. So I can put them as P0, 1 plus P1, 0. So from the table, that will be this and this. So that's 0.4. How about P2? Now, rather than writing the whole thing down, so remember P2, which means that it can happen if x0 and y2. It can happen if x1 and y1. And that's it. Why? Because x cannot be 2. We don't have a situation where x equal 2 and y equal 0. So that's the two cases that we have. So this is equal 0, 2, and 1, 1. 0, 2 is this one, and 1, 1 is this one, so it's 0.15. And let's put some space here. How about 3? 3 happens if we have x0, y is 3. It could also happen if this is x1, y2, and that's it. So that's 0, 3, and 1, 2. So that's another 0.15. And finally, P4, which happened, we have one case only when this is 1 and 4, right? 1 and 3. X equal 1 and y equal 3. So that's the only case, which is 0.1 here. All right, did I do everything correctly? Let me check. So probability total, when I add up all the values of the probabilities that I got, I should end up with 1. So if I take the distribution of any random variable, add all the probabilities, I should end up with 1. So 0.2 and 0.4 is 0.6. These two together 0.3, so that's 0.9, and finally 1, right? So now I verified that my probability distribution is correct. All right, so what was the original question? The original question is find the distribution. Okay, so we did the distribution. Okay, and finally, are the errors occur independently? So they want to verify that X and Y are independent. So if I want to verify that X and Y are independent, I have to do this for all values. I have to say P0 and 1 equal P, or test whether it's equal to P0 multiplied by P1. And I have to do also 2, 3, and so on. To prove dependence, I only need to find one case where this is not true, where they're not equal. So let's try and say, well, how about this value here, right? So let's check if P1, P00 in fact equal P0 multiplied by P1. So P00 is 0.2, right? P0 multiplied by P0, so that's for the X, and to differentiate between them, sometimes we need to do the subscript. So Px of 0 is this value, 0.5, and Py of 0 is this value, 0.4. If I multiply them together, I will get 0.2. Alright, so this value is in fact equal. Should I celebrate and say they are independent? Well, let's try another value. The other value that I can try is, let's pick another one. So let's pick 1 and 2. 1, 2 is this value here, 0.1. Let's compare it with Px1 multiplied by Py2. So from here, Px1 is 0.5, and from here is 0.3. Did I say 1, 2 or yeah, 1, 2? So this means that I'm actually looking for this number here, right? Which 0.05, 0.15. Well, obviously, this is not going to be 0.1, right? So 0.5 multiplied by 0.15, which is not, so this P12 is not equal to Px1 Py2. So I don't have to continue anymore, and I can say that x and y are in fact dependent. So this is just to show that to prove dependence, I need to find only one case where this is not true, where both sides are not equal. If I want to find independence, I have to try all values. Right. All right, let's move on to something different. So there is a concept of the expectation and the variance. Right. Expectation is the average. So if I take, let's say, if I assume that the results of an exam is a random variable, I don't really know what the results will be. Each student result is a value, right? And that value can take any number from, let's say, theoretically from 0 to 100, right? And there is a distribution. So the distribution, yes, the values can take from 0 to 100, but the distribution is different, right? So to explain the probability distribution one more time. So let's say here is my results, right? But the results, so the results can go from 0 to 100, but the distribution or the probabilities can be like this. So very, very, very few students or none will get 0, right? So the probability of getting 0 is not it's not 0, but it's low. The probability, hopefully a class, the probability of people getting something like 80 will be high. Maybe not everybody will get 100. So these are the probabilities. A probability distribution like this is hard to describe, right? I need to show a graph like this every time to describe, the distribution of marks. But if I say, and something that's everybody's familiar with, if I say the average is 75, now everybody will get it. So in probability distributions, I can find the average, or the expectation we'll call it, by multiplying each value of the random variable with its probability. So it's weighted average. In case of the in case of the heads and tails, right? Let's say the X will represent the number of heads in a coin toss, right? Just one coin toss. So X equals 0 means there's a tail. X equal 1 there means a head, right? So now if I want to have, what is the average? So the average will be X, multiplied by its probability for all x's. So this will be 0 multiplied by half, or if I want to, well, let's keep it like this, right? Plus 1 multiplied by half as well. So I end up with half. So the expectation is half. You think about it, if I toss the coin 1,000 times, the number of heads will be close to 500. 1,000 time tosses, 500 heads, right? The others are tails, right? I can also say in a game, result of a game will be red or blue or tie, right? If the probability distribution for such game is 0.2, 0.7, and 0.1, right? Well, these are the probabilities, but I want to use a random variable. So what kind of random variables I have? Let's say X represents the number of points that a team will get. So if they lose, the points will be 0. If they tie, the points will be 1. So that's for losing. This is for tie. And this is for winning. So now I converted this to random variables. So the probability of X equals 0 here, or I'll just represent it with just saying 0. So that will be, if I look at the green team, if I look at it from the perspective of the red team, okay, the red team perspective, their probability of loss is 0.7 because the blue team wins. The probability of them tying is 0.1, and the probability of them winning is 0.2. Right? On average, let's say I want to find on average what is the number of points that the red team will get. So here, for every loss, so it's 0 points they get with a probability of 0.7. For tying, they will get 1 point with a probability of 0.1. And for winning, so they must be not a very good team, right? So they have a low chance of winning. So this means that on average, the average point that they will get is 0.1 and 0.4, 0.5. All right, so that's the expectation. You can say same thing with or use similar to that example for marks, and you get, even though I can find the average, but assuming that I didn't do the exam yet, based on previous experience, I can say, well, the probability of students will get 100 is such, and probability of getting 50 is such, and I'll find the expectation, right? So the expectation, as I said, if you look at all the values and their probabilities, the expectation is the average, or the weighted average of all of this. Okay, um, but the average or the expectation itself, which is given mu or E of x, by the way, it is the average or the expectation is not random number. Is not random, right? So even it is the expectation of a distribution but itself it's not a random number. Expectation by itself does not tell the whole story. How? Okay, so let's say back to this distribution. If I guess where the average is, I will say it's somewhere here, right? How about if the distribution looks like this? Still the average, still you can guess that it's the green line. But in both cases, the average is the same. But I can't tell, so the first example, there is a wide range for the marks. In the second example, the marks are close to the average. So if I say, well, the average, my expectation that the average mark will be 70. Does that mean that most marks will be somewhere between 60 and 80? Or they will be distributed between 40 and 90? Or 40 and 100? You could also find a situation where most of the marks are concentrated somewhere around the average, but there are some outliers, some people who are getting really, really high marks, and some people are getting really, really low marks, so they kind of average themselves, right? So the high marks and the low marks, uh, and you will get the average that's actually it is the average, but it doesn't give you the full picture. So for that, we need to find another piece of information from the distribution, which is the variance. The variance tells me more information, which is how far the uh, the marks from the expectation, or the other variable of other values of the random variable from the expectation. So you could explain the situation with variance. In this case, the variance could be, let's say hypothetically, here between these 2 points, while in the first example, the variance will be here. So if I give you the average or the expectation and the variance, you will get an idea about how far or how concentrated the marks are, right? So the variance is calculated by, or given the simple var x, and it's calculated by subtracting the expectation from the random variable and taking the square, right? So if I want to do it, it is var x is the expectation of x minus mu. Mu is the expectation, square, right? So that's what we're talking about here. And since it's the expectation, so the expectation is, so you replace this part, you put it or substitute it with x or for x. So x minus mu square px. So what's the variance of the game here? We calculated the expectations, that's mu. So what's the variance? Okay, so var x here is, let's take the first value, which is 0 minus mu 0.5 multiplied by um, the probability of losing here, which is 0.7, plus, forgot the square, don't forget the square, 1 minus 0.5 square multiplied by the tie, which is 0.1, and 1 minus 2 minus 0.5 square multiplied by 2. First thing you notice that all the numbers will be positive, right? Because we have the square. So here 0.5 squared is 0.25 multiplied by 0.7. So probably I will just use my calculator here. So 0.5 square 0.7, that's 0.175 plus 0.5 squared, that's 0.25 multiplied by 0.1, so that's 0.025, and this is 1.5 squared multiplied by 2.2, get 4.5. I'm just gonna double check everything because I may have made a mistake here. Okay, it's the square, not the square root. Yeah, 0.45, and the middle one is 0.5 square. All right, so if I add all of these values, it's 1.225. So the variance is 1.225. Assuming that I did all of my calculations correct, which I don't think so. I think I missed one there. 0.175 plus 0.425 plus 0.45, 0.65. Okay, so that's 0.625. So the variance, the expectation is 0.5 and the variance is 0.65. And the variance is given the simple sigma square. This number is a random number, right? Unlike the expectation is not a random number, so it's always fixed. This is a random number. Because it's square, we can get the square root of it, and we'll call that the standard deviation. So the variance is the square number here. The standard deviation is sigma, and the standard deviation is just, we'll take the square root of 0.65 here, and we'll get 0.806. And be careful between, or you have to differentiate between the variance and the standard deviation, and if you, I may even sometimes get things mixed up when I'm talking and they when I speak about uh, variation or variance when I'm actually talking about the standard deviation. So one is the square of the other, right? Or one is the square root of the other, depends on which one you're talking about. Okay, so let's review what we learned so far. We learned about the expectation, and we learned and remember the mu, which is the simple or the expectation of x. We talked about variance and standard deviation. So the variance uh, is this formula x minus mu squared multiplied by p of x, and you take the sum. It can be simplified actually by using this formula. So the variance will be the expectation of x squared minus mu squared, which by itself, if you think about it, is this, right? So both of them can be written either way. If I want to repeat the same exercise here using x squared instead of the subtraction here, I can do it by saying e x squared is the sum of x squared p x. So that is 0 square multiplied by 0.7 plus 1 square multiplied by 0.1 plus 2 square multiplied by 0.2. This could be easier to calculate, right, and less problematic or less susceptible to errors. So that's 0, that's 0.1, and that's 4 multiplied by 0.2, so that's 0.8. So that gives me 0.9, and mu square mu is what did we do mu earlier? 0.5. So mu square is 0.5 square. All right, so the variance then is 0.9 minus 0.25. Does it give us the correct answer as before? I think it does. So that's 0.9 minus 0.25, 0.65, which what we got earlier. Now you'll find that actually this formula is easier, right? So it's easier than the subtraction. Okay. Before I get to the topic of covariance, let's go back to the expectation of function. Right? So to explain it simply, let's assume again that the winner, or at the end of the tournament, you get a reward, financial reward. So for every point you earn, you get $1,000. So let's say for X, that's X represents the result of the game, right? So let's say Y represents the winnings. So that will be 1000x, $1,000 for every point. So you lose, you don't get money. You tie, you get 1,000. You win, you get 2,000. So what is the average winning or the expected winning of the team? And for the example that we chose, which is the red team, we could say that the expectation of y is the sum of y px, right, for all x, and this will be 1000 x px. And this is the same as saying that I am getting the expectation of this function, of a function of x, right? Y is a function of x. So I am practically doing this. All right, there is an easy way to the g of x, or the function of x, can be anything. Can be something simple like multiplying a constant, or it can be more complicated. Right? If it's something simple, this is similar to the expectation of a of x, where a is the constant 1000. So we could simply take a out, and it becomes the expectation of x multiplied by a. So the winning for the team, we know that the average will be the average is 0.5. So the winning will be 1000 multiplied by 0.5. We get 500. So the expected winning of the red team is 500. You have here the properties of expectations, where this is multiplying a constant by x. The expectation of a constant is the same constant. So there is no randomity or random at all. So the expectation of the number 5 is number 5. If we have something like this, it's a linear function, so we can break it down. So the expectation of ax plus by plus c, we can break it down to its component, and we will get simplification, right? If x and y are two independent variables, their expectation, the expectation of the multiplication of x and y, is the multiplication of the expectations, right? So the expectation of the multiplication is the multiplication of the expectation. Try to repeat that 3 times. But we cannot use this property to verify independence. So you cannot just say, if I give you a joint probability distribution and the expectations, you cannot just use this formula and say, oh, they are independent. No, you have to go back to what we talked about earlier and try every situation, or prove dependence, right? Because sometimes the averages actually become true, or this formula becomes true even if they are dependent. So we cannot rely on it. Right. The last concept here is the covariance and the correlation. So let's say to back to our example of the CPU and memory. So every time the CPU go up, the memory will go up in a computer, right? Not necessarily exactly the same. As I said, the CPU can go up because it has a big software, it's working hard, or it could be because it's crunching numbers, right? And the numbers are, if it's doing complex mathematical formula, it may not take a lot of memory, but it take a lot of CPU time to calculate. So the CPU and memory, they may be having a relationship between, like, every every time one increases, the other may increase, but it's not exactly the same. It's not like you're going to see one increases so the other one follows exactly. So there is a relationship, but we don't know exactly whether the relationship is, or how tight the relationship is. And this is what the covariance tells us. If we see graphs like this, we could say, even though the two graphs are not identical, but we could say, well, seems like if one goes up, the other one goes up, right? But if we see something like this, we may not see a good relationship between the black and the red, right? Or the red and the green. So random variables, they may to measure the relationship between them, we use the covariance. And the covariance is given by this formula where it is the covariance of x and y is the expectation of x multiplied by y minus the expectation of x multiplied by the expectation of y. Okay, now notice that, um, or we were told that if the covariance is greater than 1, greater than 0, means that x and y are heading in the same direction. So if x increases, y increases as well, right? It may not be at the same rate, right? So one could go this way and the other one could go this way. But you see that one increases, the other one increases. If the covariance, so in this case, the covariance is greater than 0. If it's the other way around, let's say something like this. So here the covariance will be less than 0. It's one increases, the other one goes down, and vice versa, right? So every time that the CPU goes, or the heat is up, the performance goes down. They are correlated. There is a covariance less than 0 between them, right? Okay, covariance can be a big number. And if I say, well, the covariance between x and y is 70, you don't know, is 70 means a big deal or small, right? Because the covariance can go 100 and 100,000, right? So 70 is could be small relative to 100,000, right? So we don't really know. It's just a number that it's, if it's positive, there is a relationship between the two of them. One increases, the other one increases. If it's negative, then it's the other way around. If total 0, this means that they are uncorrelated, right? If we want to limit, if we want to know how big the relationship or how small the relationship between the two, we need the correlation coefficient. So the correlation coefficient take covariance x and y divided by the standard deviation of both x and y, right? So, and we give it the simple here raw. So covariance x and y divided by sigma x sigma y, or the standard deviation. This number here goes between -1 and 1. It's always between -1 and 1. So here we'll say if it's 1, it's totally correlated. So the two variables are totally correlated. If it's -1, they are correlated as well, but on the opposite side. So if one goes up, the other one goes down. If it's close to 0, they are weakly correlated. So if they are close to 1 or -1, they are strongly correlated. If they are close to 0, they are weakly correlated. If they are 0, they are not correlated at all. They are uncorrelated. And if they are 0, so remember when we talked about the covariance, x and y is the expectation of x, y minus wx, wy. And we also said that if they are for independent x and y, this is true. Exy equal exey, right? So if x and y are independent, then exy can be substituted by mu x mu y minus mu x mu y equal 0, right? So for x and y, for any independent independent x and y, there is no correlation between them, which makes sense, right? The correlation will be 0, so they are uncorrelated. Okay, so all of this talk about correlation and mu and sigma and all of this. So what is the application? Right? So there are many applications. Some of them are statistics, some of them probability, and one of them is that maybe is of interest to us is calculating risk. Right? So calculating risk of failure of a device. Let's say the device CPU is load can be a random variable, right? I'm not sure how to draw it. So a random variable, the random variable can take any number in this range. Right? So this is the CPU load, right? And there is a probability for each one of these values. But if the CPU load goes up to a certain limit, it may fail, right? It may fail, the router may crash, so there is a failure. Right? So I am going to be interested in what is the probability that the CPU load exceeds certain limit. That's one scenario. Another scenario, let's say I have a link that has a bandwidth, right, specific bandwidth, and the traffic goes up and down. If I consider this, if I consider the utilization of the link at any point as a random variable, I may be interested in what is the probability that the link or the bandwidth exceeds the capacity of the link. So now packets can be dropped or there will be congestion. So again, what is the probability of, having a lot of data bursts that we will exceed the allocated bandwidth for that specific link? So one of the applications is we're calculating risks. Okay, so as I said, sometimes we don't know what the distribution is. I cannot say that the CPU load is given by this distribution, or that the bandwidth follows certain distribution. Sometimes we do, sometimes we don't. This person, Chebychev, came up with a useful inequality that says that I can actually calculate if the probability of exceeding a certain limit without knowing what the distribution is, right? By applying this formula here. So the probability of magnitude x minus mu greater than epsilon, the probability of this is less than or equal sigma divided by the epsilon square. So it seems like a little bit scary, but actually it's not. Epsilon is any constant, right? Mu we know is the average. Sigma is the standard deviation. So if we figure out the standard deviation and mu, which we don't, all we need to do for this is calculate statistics, right? We'll calculate statistics, we'll find what the mu is and what the sigma is, even if we don't understand or we don't know exactly what the distribution is. We can find these two. If we find these two, we can find what is the probability of exceeding a certain limit. Right? So here we'll do an example. So let's say, suppose the number of errors in a new software has expectation mu equal 20 and the standard deviation sigma equal 2. According to the Chebychev inequality, right? We need to figure out what is the probability of having more than 30 errors. So I will take this step by step. And so the Chebychev inequality tells me that the probability of x minus mu magnitude less than or greater than epsilon. So this probability will be less than or equal sigma over epsilon square, right? And by the way, when you see the magnitude, it means that actually we are calculating if this is the probability distribution and this is mu, right? We are calculating probabilities that the values exceeding these two limits, right? So this is epsilon minus epsilon plus epsilon. It depends on what the mu is. So mu minus or plus epsilon and mu minus epsilon. So we're calculating the probability of values beyond these two lines, right? So let's go back to the question here. It says that what is the probability that the errors exceed 30? Right. So let's go back here and say, yeah, we want to find out if the errors, what's the probability of errors exceeding 30? We have mu of 20 and sigma of 2. Mu is 20 and sigma is 2, right? So I need to find out this, but I have this formula here. So I need to sort of make these two equal, right? So if I rearrange things, so let me write x minus mu greater than 30 minus mu. So what I did, I just subtracted mu from both sides. Right. So if I continue, so this is equal x minus mu greater than, mu is 20, so that becomes 10. So this becomes epsilon. If you compare this with this function, this is epsilon. So I got my epsilon. So now sigma is 2 divided by epsilon, 10 squared. So this is 1 over 5 squared, or 1 over 25. So the probability of x greater than 30 is 1 over 25. Well, let's see what the answer is in the, so it's 0.04. Okay. So this is summarized in one line, but I just showed you the steps. So x greater than 30, I subtracted both sides by mu. I got epsilon, so now I used it in the right side and I got the result. Okay. So that concludes the first part of this chapter, and we looked at the concept of random variables. We looked at probability distribution and cumulative distribution function, CDF. We looked at joint distribution, marginal distribution, independence. We also looked at the expectation or average, variance, covariance, and correlation, also standard deviation there. And finally, we talked about Chebyshev inequality. So that will stop. I will stop here. Then in the next recording, I will start talking about the families of discrete distribution. So we looked at probability distribution in general, and we looked at examples, that some of them in the notes, some of them I created myself for simple probability distributions. But we have a lot of well-known probability distributions that are useful for many applications. So we'll talk about them next. So until then, thank you very much. I will see you next.